Hello everyone, welcome to Structural Insights. This lecture is about the sharing of loads in slabs on the beams. So we have one-way slab, and we have two-way slabs. In one-way slab, we have this Ly as the longer side. In two-way as well, we keep Ly as the longer side, and then we have Lx as the shorter side. So the ratio of Ly by Lx is checked, and this has to be greater than 2 for one-way slab, and Ly by Lx has to be less than or equal to 2 for two-way slab. So this is the basic classification. Now how the loads comes on the beams from the slabs, that we'll see. So here you see this shaded portion, right, dark pink color. This load will come on Ly, this span, right? So this is the span. Okay, on this span this load will come. Okay, so Ly will take half of the length of Lx on in the slab. Okay, this is how the one-way slabs are designed, and what we'll do in design, it's very simple. Suppose this is a longer beam, Lx length, and this is the load. So what will the load intensity? These are the supports. Okay, so suppose this is the load intensity is W kilonewton per meter square. Okay, and this is Lx. So what will be the intensity here? So remember, the intensity on the beam is not in terms of kilonewton per meter square. In beams the intensity is kilonewton per meter. So to convert this kilonewton per meter square to kilonewton per meter, say this intensity on the beam is W dash. Okay, so W dash will be W into Lx by 2. So this W is in kilonewton per meter square, and per meter square we multiply by meter, so this unit will be kilonewton per meter. So once you have this beam and this UDL loading, you can obtain the bending moment diagram. So okay, so you can obtain the bending moment diagram. It depends what are the supports condition you are taking, but suppose it is simply supported. So once you have bending moment diagram, and based on this bending moment diagram, we can actually obtain the maximum moment. For the given maximum moment, you can provide the reinforcement based on IS 456-2000. Okay, this is how one-way slabs are designed. Now let's come to the two-way slabs. In two-way slabs, what happens is that load is distributed in terms of triangles and trapezoids. So this angle is 45 degrees. So what we do is we have a two-way slab, and we start drawing these lines at 45 degrees. Okay, everywhere, and they will tend to meet at some point. Okay, this will meet at some point, and these points we connect. So this much load will come on this slab, this load will come on this beam and this beam, and then this load will come on this beam, this load will come on this beam. Okay, so this is how the load is shared between the four beams in a two-way slab. Now we have to see what is the load in terms of kilonewton per meter on a slab, on a beam from a given slab. So let's start with this Lx. This Lx is here, this one. So how do we transfer the load from this slab to the beam Lx in terms of kilonewton per meter? So what is W dash for Lx? So what is the normal tendency of solving this problem? So let's divide this. So what we have, see, we have this type of loading, right? This is in W kilonewton per meter square presently. This is an area load. This is like this now. Okay, this is Lx. So what we will do is, the normal tendency is And this one, how much is this one? Anybody? What is this one? This is Lx by 2. Okay, because this is 40 degree angle, no? So this is halfway here. So this length, and this length is equal. Okay, this is 40 degree angle. So this is Lx by 2. So this is also Lx by 2. Okay, so this is Lx by 2. Okay, so what is the normal tendency? Normal tendency is what we'll do is, we'll just evaluate the area load and divide by the length of this beam. So area load is half of the base into Lx by 2 area. This is the area of this triangle. So what is this value? This is Lx square by 4. And what is the length of this beam? Lx. So what people do is they divide this by Lx. So we get Lx by 4. And W is anyway multiplied. So is this correct? No, this is not correct. Why? Let's see. So let's see. So we have this beam. What is actually happening is this is W per meter square, and this is the width of the slab considered is Lx by 2. We have to imagine an equivalent beam with same width but rectangular in dimensions. So we are imagining that this load and intensity effect of on the beam because of this load intensity because of this loading is equivalent to load intensity because of this distribution. So we have to find out an equivalent load on this beam. So this is load intensity. Okay, this is the width of the slab is same as Lx by 2. So suppose this is W1. Okay, I'll write again. See, this is W1 and this is W. Okay, so we have to find out maximum bending moment here. Okay, so this maximum bending moment because of this loading should be equal to the maximum bending moment here. Okay, so while equating these two bending moments, we will get a relationship between W and W1. So let's just do it quickly for this left side beam. So this is say R. So what is the value of R? R will be half of this loading. So this loading is W into half into base. This is Lx into Lx by 2. So this is the area loading, and we want half of that for R. Okay, and for bending moment, what we'll do is we will take the effect of this area load and its moment here. This is clockwise, so we'll get, say this point is 1, this point is 2. So M1 will be equal to R into Lx by 2 minus this triangular loading, half the triangular loading into base Lx by 2 into 1 by 3. So this is Lx by 2 is CG is here. This is 1 by 3 of Lx by 2. Okay, so here it is acting like this. So that's what we are evaluating here. So we have W Lx cube by 16 minus, what is the triangle area? X cube by 16 into 2 by 3. Okay, so what is this value? This is WLX cube by, we can actually write 8 into 1 by 3. Okay, we are not multiplying this just for the time being. Okay, now let's come here. We want to evaluate M2. So what is this reaction? Reaction is equal to is this is W1 into Lx into Lx by 2. This is the area of the rectangle. This is the area of the rectangle. Okay, now we want half of that. For this reaction we need half of that, okay, because there are two reactions. So this is 1 by 2. Okay, so what is this value? WLX square upon 4. Okay, now what is this value here? Suppose we want half of this rectangle for this rotation. What is this value? Anti-clockwise. So this value will be, suppose I'm just evaluating the moment because of this shaded half rectangle, then this area of this rectangle is, this is anyway Lx by 2. So W into Lx by 2 into Lx by 2. This is the area. And what is the lever arm? Lever arm is Lx by 2 into 1 by 2. Okay, because lever arm is at the center. Okay, here is the lever arm. Okay, center. So let's evaluate the bending moment at 2, which is equal to reaction R, which is W Lx square by 4 into its lever arm, which is Lx by 2, minus area of the rectangle, which is WLX square by 4 into lever arm of the rectangle, which is Lx by 4. So this value will be WLX cube by 8 minus WLX, what is this, Lx cube by 16. So you get this WLX cube by 16. When we equate this value, so we have this value M2, and we have this value M1. So now we'll equate M1 and M2. So let's do that. M1 is equal to M2, WLX cube by 24 is equal to W. This is everywhere, this is not W, this is W1. Alright, just don't get confused, both are different because one is triangular loading, one is rectangular loading, so that's a difference. So we have to evaluate what is W1. So 8 2 16, 8 3 21. Lx cube. So W1 is equal to 2 by 3 of W. Okay. Now this is the area loading. Okay, both of these W's are in kilonewton per meter square. So what we need is, we want this loading on this beam in terms of kilonewton per meter. To convert that into kilonewton per meter, we have to multiply by the width of the slab, which is Lx by 2. So if W1 is equal to 2 by 3 of W, so what will be the W2? W2 is nothing but the line load on the beam. So line load will be 2 by 3 of W into Lx by 2. Why Lx by 2? Because this is the width of the slab and this is the area loading. Okay, so this is WLx by 3. Okay, this is the final answer. So there's nothing very difficult to understand. It's very simple. If there is any difficulty, you can anyway ask, but that's how it is. Always you will see in the text that the load on the triangular portion on a two-way slab is WLx by 3. So this value here is WLx by 3. On this beam, the line load is WLx by 3. Here also it is WLx by 3. In a similar fashion, we can evaluate the bending moment on this, line load on this beam by equating this trapezoidal load, bending moment to this trapezoidal load, to an equivalent rectangular load, and we find out the intensity of that rectangular load, and then we distribute this rectangular load as a line load on the beam by multiplying with the width of the slab. So that's how it is. If there is any difficulty, kindly contact. Thank you so much. If you like this content, kindly subscribe. Thank you so much.